What problem does BP primarily solve in tokenization? A. Out-of-vocabulary words. B. Computational efficiency. C. Memory usage. D. Training speed. The correct answer is A. Out-of-vocabulary words. BP is chosen because it's like having a universal translator that never gets stumped by new words. Traditional tokenization fails when it encounters words not seen during training, but BP breaks any word into smaller, familiar pieces. Think of it as solving a puzzle. Even if you've never seen the complete picture, you can still understand it by recognizing the individual pieces you know. To remember this easily, think BP equals building pieces everywhere. It builds vocabulary by finding the most popular character pairs, ensuring no word is ever truly unknown. Which tokenization method is used by most modern LLMs? A. Word-level tokenization. B. Character-level tokenization. C. Subword tokenization. D. Sentence-level tokenization. The correct answer is C. Subword tokenization. This is the Goldilocks solution of tokenization. Not too big like full words, not too small like individual characters, but just right. Word level creates huge vocabularies and can't handle new words. Character level loses meaning and is computationally expensive. Subword tokenization captures meaning while handling any possible input, which is why GPT, BERT, and other modern models all use this approach. Remember it like a Subway sandwich, perfect-sized pieces that make a complete, meaningful whole. Each piece is substantial enough to carry meaning but small enough to be flexible. What is the typical vocabulary size for modern LLMs? A. 10,000 to 20,000. B. 30,000 to 50,000. C. 100,000 to 200,000. D. 500,000 plus. The correct answer is B. 30,000 to 50,000. This range represents the sweet spot between coverage and efficiency. Too small, and you can't handle language complexity. Too large, and training becomes unstable and expensive. Modern models like GPT use around 50,000 tokens, while BERT uses about 30,000. This is actually similar to human vocabulary. We actively use 20,000 to 35,000 words, but understand about 70,000. Think of it as the perfect toolbox. 30 to 50K equals the perfect sweet spot. Like a chef's knife set, not too few tools, not too many, just right for any recipe you want to create. How are token embeddings typically initialized in transformer models? A. All zeros. B. All ones. C. Random normal distribution. D. Precomputed word vectors. The correct answer is C. Random normal distribution. Starting with random values might seem counterintuitive, but it's actually brilliant. If all embeddings started the same, they'd all learn the same thing. Random initialization with normal distribution gives each token a unique starting point to develop its own personality. Through billions of training examples, these random numbers evolve into meaningful representations where similar words end up close together in the embedding space. Remember this as random start, smart finish, like learning to walk. Random steps become coordinated through practice. Every expert embedding started as random numbers that learn their purpose. What is the purpose of the CLS token in BERT? A. To mark the end of sequence. B. To represent the entire sequence. C. To separate sentences. D. To mask tokens. The correct answer is B. To represent the entire sequence. The CLS token acts like an executive summary of your entire input. While other tokens focus on their local context, CLS gathers information from the whole sequence through self-attention. By the final layer, its embedding contains a compressed representation of everything, making it perfect for classification tasks. It's like having one person attend every meeting and then give you a complete briefing. Remember, CLS equals class summary, SEP equals separator, mask equals hidden mystery. Each special token has a specific job, and CLS is the summarizer that captures the big picture. What is typically frozen during fine-tuning for downstream tasks? A. All parameters. B. Only embedding layers. C. Nothing, full fine-tuning. D. It depends on the approach. The correct answer is D. It depends on the approach. The freezing strategy depends on your data size, computational budget, and task similarity. With limited data, freeze most layers to prevent overfitting. With abundant data, you can afford to fine-tune more layers. It's like teaching a skilled musician a new song. If they only have one practice session, focus on the melody. If they have weeks, they can master every nuance. Think more data equals less freezing. Like cooking, more ingredients let you customize more of the recipe. Start conservative with freezing, then gradually unfreeze as your data and compute budget allow. What does LoRA add to existing model weights? A. Diagonal matrices. B. Low-rank decomposition matrices. C. Random noise. D. Scaling factors. The correct answer is B. Low-rank decomposition matrices. LoRA is genius in its simplicity. Instead of updating a massive matrix with millions of parameters, it adds two smaller matrices that multiply together. A 4096 by 4096 matrix has 16 million parameters, but two matrices of 4096 by 64 and 64 by 4096 have only 524,000 parameters. That's 97% fewer. Yet this achieves nearly the same performance. Remember, LoRA equals low rank, amazing results, like finding a shortcut that's actually better than the long route. It proves that most changes needed for adaptation can be captured in a much lower dimensional space. In prompt tuning, what is optimized while keeping the model frozen? A. All model parameters. B. Only the last layer. C. Learnable prompt embeddings. D. Attention weights. The correct answer is C. Learnable prompt embeddings. Prompt tuning is like having invisible instructions that guide the model without changing its core. Instead of modifying billions of parameters, it learns a few special embeddings that get prepended to your input. These soft prompts act like secret codes that tell the frozen model exactly what task you want it to perform, achieving most of the benefits of full fine-tuning with a fraction of the computational cost. Think of soft prompts as invisible instructions, like having a magic phrase that makes the model understand exactly what you want, without teaching it a whole new skill set. How does in-context learning work? A. By updating model parameters. B. By providing examples in the input. C. By modifying the loss function. D. By changing the architecture. The correct answer is B. By providing examples in the input. This is perhaps the most remarkable capability of large language models. Show them a few examples of a pattern and they instantly understand what you want without any training. It's like showing someone how to solve one math problem and watching them immediately solve similar problems. This emergent ability only appears in very large models and demonstrates a form of intelligence we're still trying to fully understand. Remember, show, don't train, like teaching by example rather than writing an instruction manual. The model sees the pattern and applies it immediately, just like human intelligence works. What type of data is used for instruction tuning? A. Raw text. B. Question-answer pairs. C. Instruction-response pairs. D. Code repositories. The correct answer is C. Instruction-response pairs. Instruction tuning transforms a language model from a text predictor into an instruction follower. Using thousands of diverse instruction response examples, models learn to understand and follow human commands rather than just completing text. This is what makes the difference between a model that finishes your sentence and one that actually helps you accomplish tasks. Think of instruction tuning as teaching good manners, like training a model to be helpful, harmless, and honest. It's the difference between having a parrot that repeats words and having an assistant that understands what you need.